paper that we are going to see today, it's a very, one can say, influential paper. Huge amount of work is actually being done depending and using the work that's being proposed by them. So Ashish Vaswani is the main author, and there are so many other persons. So you can also understand that all the big papers, good papers, they are going to have not one or two authors, but they are having multiple authors, and these multiple authors, they are going to contribute equally, or maybe two or three persons are contributing more, and then they come up with something which is really, really important. Let me tell you that this attention is all what you need. Is the first paper in which they have proposed this network and the transformer. If I say that the transformer network, this is that network in which the first part is actually the first part is the encoder and the second part is the decoder. And now you can understand that input embedding is there, which is coming and going in, and then position embedding is also going to come, and that is the thing today we are going to see. But adding both of these input and positional embeddings, they are going inside the transformer network, or one can say the transformer layers or the blocks which are actually being there, in which you are having multi-head attentions and so on. So don't worry, I'm going to talk about them one by one. I just wanted to show that whatever that we have covered so far, things are directly coming from these spaces. Attention, you can see that query, key, and value we have seen, and you all understand that query and key got multiplied to each other and being normalized by the dimension, and softmax is being done, and that becomes the contribution of that value, and you multiply that. So that is the actual attention that they are saying, that this much amount of attention one should be giving to that value, or the or that input. That much amount of attention need to be given to that set of input. And then multi-head attention, we have seen that multi-head attention. Soon I am going to show that attention to you again. From this we are going to start. So why I have shown all this stuff in this paper is that whatever I am trying to teach from my notes and different blogs, they are directly coming from these raw, one can say, papers, which are, why I'm saying raw, because if you read from there, these are being written for the researchers, and whatever the way we are teaching, they are actually being shown to you in terms of normal students. So that's why we make several things very easy, but essentially they are very complex and require so many other things along with that. So those who really got interested, understood the concept one by one, I definitely encourage you all to read this paper. Yes, so this is the query, this is the key, and this is the value, and query and key got multiplied, softmax, and multiplied by the value. That is the self-attention. We all understand that why we require to be this product to be normalized with this dimensionality of the vector. And yes, so the multi-head attention. Okay, so this is the thing. We have talked about this multi-head attention, in which teacher gave homework to the student gave homework to the teacher. That gave, both of them are same, but we are saying that okay, in different contexts the same word is going to behave in a much more different way. So is there a way by which I can somehow manage this? So it is the they have said that instead of learning only one such context, because this is one context, means that three matrices you are learning, you can learn instead of three, you can learn, this is actually being said as one head. Say that, then we say that instead of having head 1, which is having these three things, I'm having head 2 and head 3. So you can have 3 heads, and your inputs are going into 3 heads, you are getting 3 outputs, and somehow you try to combine them using some neural network. These things can actually be combined, And instead of getting multiple copies of Y or the 3 copies of Y, neural network can learn that what is the best possible aggregation that I do so that to get the best Y1, which is very close to my output that we want actually. So basically, in case of attention, what you are doing is that it's going to be a one-to-one type of transformation, that for each x1 probably we are having this y1, for each x1 we are having from y1 and y2 and so on. And later these things can actually be used to predict and to do classification, or soon we are going to see that. Is there any doubt up to now? I assume that we have seen up to this thing. Yes, okay, fine. Now I'm going to talk about another thing that is called as, so multi-HUD attention we have seen. There is something which is called as narrow and wide self-attention. What does that mean? Is that suppose that your input dimensions are 256 dimension. I'm having 256 dimensional word to vec embedding or whatever the place where you are working. So I'm having 256 such embeddings possible with me. And one way is that over that I am going to apply over this 256 dimensional vector, I'm applying directly a wide head attention mechanism. So how many? So let us see, ask someone that what is going to happen over here. Several students are right now missing. Ananya, can you listen? Ananya, can you listen?
Hello.
Yes, Ananya, can you listen?
Yes, sir.
Yes, so Ananya, what I'm saying is that we are having a 256 dimensional input vector like this. Yeah, here I have shown 8 values, but do not worry about that. This is 256 dimensions, 256 dimensional vector, right?
Okay.
Okay, over that I am going to apply a attention head. So first of all, tell me that how many matrices are going to be there in one attention head?
Sir, 256 cross 256.
But how many such matrices in one
Okay.
attention head?
So 3.
One attention head, how many such matrices? 3. Why?
So 3. So query key and value.
Query, key and value, correct? So you are going to have 3 such matrices, query, key and value. Each matrix is going to be of size 256 by 256. Yes, Ananya, that's clear?
Yes, sir.
Okay. So if I take this, and that is why it is called as a wide head. It's a wide head because it's looking to each and every one. Now the point is that what is going to be the number of parameters that you need to learn is going to be 256 multiplied by 256 multiplied by 3.
3. Yes.
Clear?
Yes, sir.
Okay. And suppose that I am having 8 such heads. Suppose that I am having 8 such heads.
Okay.
Then this much.
Into 8. Yes.
Yeah. So it's going to be 2 power 8. This is 8. Plus this is also 8. And
Yes.
plus this is
3.
also 3.
3.
So total number of parameters are going to be 3 multiplied by 2, 8 to
Yes.
16, 17, 18, 19. This is clear?
Yes, sir.
Okay, Ananya. Thank you.
Thank
Now you
you.
can go.
Thank you, sir.
Now let me ask Vaibhav. Vaibhav, can you listen?
Yes, sir.
Yes, Vaibhav. Now you see that this was the wide attention. You all understand what is wide attention.
Yes, sir.
Wide attention means that I am applying attention over the full input, all the input dimensions. Yes.
Yes, sir.
Now what you can see is that yeah. So suppose that if I'm going to divide this whole thing into a chunk, basically chunk of 32 dimensions. So first 32 dimensions, this is first chunk, second chunk, third chunk, and so on. So I'm having 8 such chunks. Fine, Weber, this is okay.
Yes, sir.
And that is what I have shown, that this is my chunk number 1, which is having 32 things, 32 things, 32 things, 32 things, and so on. And over each of these 32, I am applying one head.
Yes, sir.
So if I apply one head over this, then you are going to get one output. Is that clear?
Yeah. Okay, sir.
This one output is going to be there. And how many such inputs are there? Input number 1, input number 2, input number 3, input number 4, input number 5, and so on.
Yes, sir.
So, so if I take this, apply one chunk here, output 1 is coming, output 2 is coming, output 4 is coming, and all of them are actually coming one by one. That's okay. Now the point is, how many heads do I require? I require 8 such heads. Yes.
Yes. Yes, sir.
When I require 8 such heads, my also have to be how much? This is my input. Then output also have to be what size?
Sir, we are taking 8 chunks, then our output will be 8 different outputs for 8 different heads.
Yeah, for 8 different heads, 8 different outputs, and if I concatenate all of them, the size becomes equal to this.
And yeah, size will be equal to the input
Yes,
size.
so this is my input, this is my output, and output size is also same as the input size, because what is this? This is one data point. So one head in wide head, you apply this head over this full data point. In narrow head, you divide this data into multiple parts in narrow, and when your attention becomes narrow, you apply individual heads, one head to this, one head to this, and so on. So in this way, how many heads you are having? 8 such heads. Now what is going to be the dimensions of that head? How many matrices are going to be there in that head for this?
Okay,
How many matrices? Yes?
sir, 8 different matrices of
8, not, yes.
Sorry. Yeah, for 32 cross 32 dimensions.
32 cross 32. And how many such things in one head? 3. And how many such
Yes,
heads?
sir.
8. Clear?
Yes, sir.
Yes.
Yes,
So
sir.
we are, so this is my narrow, and in my narrow I am having 32 by 32 multiplied by 3, that is in one head. And how many such heads? 8 such heads. So if you have wide head, then this is the number of dimensions. If you have wide head, then these are the number of dimensions. If it is narrow head, then this is the number of dimension. What it is? It is 2 power 5 plus 5 plus 3 multiplied by, that's multiplied by 3. This is equal to 3 multiplied by 2 power 13. So it's far lesser than the wide head number of parameters. Yeah, it's also okay that you have far lesser than that thing, that is useful for you. But wide was actually learning the full relationship between the input dimensions, and the negative part of this narrow head is that it is only looking within this, it's not going out that. So if there is some relationship which is happening over here, it's probably not being able to explore that relationship. Understood?
Yes,
Weber? Yes. So
yes, sir. Understood.
understood. And the other point is that The number of parameter is far less in the narrow head. Now let us ask someone else. Anurag. Anurag, can you listen? Anurag, are you there? Anurag is not there. Akanksha Tyagi. Akanksha Tyagi, can you listen?
Yes, sir.
Akanksha Tyagi, you are in which branch? CS? You are
Sir,
in C?
sir, I am in PhD.
Akanksha Tyagi in PhD. You are doing my course, but I assume that are you attending all of my previous lectures?
Yes, sir, I had made you also. I had informed you, sir, about my situation at home. Sir, I had
This
made
is
you
okay.
also many a times. Sir, I had been listening to the recorded lectures.
Recorded. That's okay, Akanksha. Fine. Are you comfortable to answer something, or it is your first lecture of transformer?
Sir, transformer is the first one.
Transformer is the
And
first one. I understood. Understood. Okay, no problem.
yes.
Let us go. Prateek. Prateek.
Yes, sir.
Yes. So Prateek, you understand the pros and cons of wide and narrow
Yes, sir.
head. Now the point is that suppose that if I have for each such thing, for each one chunk, I am having one head. Now instead of that, if I have three heads, then can you tell me that what is going to be the number of parameters that I need to learn?
Okay. So there are 32 cross 32, 332 cross 32 matrix.
Yes.
Now because there are three heads, so further multiplied by 3.
Suppose that I am having 8, make it 8. That is better, right? 8.
Okay. And then since we have 8 such outputs, so yes.
Yes. So let us see, it's going to be 2 power 5 plus 5 plus 3 plus 3 multiplied by 3. That's going to be equal to 2 power 16 cross 3. So still it is better. Better than this. Far
Sir,
better than this.
Sir, I had a
Yes.
doubt.
Yes.
Sir, this 256 dimensional input vector that you are saying,
Yes.
so this is with respect to a word, or it is an embedding of a sentence or something.
Yes. Yeah, this is with respect to a word, Pratik.
Sir, so because till now, whenever we looked at this, we looked at a sentence like I am going somewhere or something like that.
Yes, yes.
So, so my question is that if we are just looking at a word, so currently we are sort of putting the attention network
Oh, you are
the
saying that
letters.
individual word? No. So in the case of narrow, yes.
Right, sir.
In
So,
the case of narrow heads, what will attention to? Yes.
sir, your voice is a little breaking.
My voice is breaking. Yes, I know, and that is actually because of this internet. I'm very sorry for this. Yes, please say Pratik again.
Yes, sir. So the doubt is that say I have a word, suppose say excellent. So
Yes.
currently we are trying to put the attention on the letters of excellent, if I'm not wrong. So EX, something like that.
Yes. So in the case of narrow heads, probably this is happening that you started to give attention to the word, individual letters. But
Right.
in the case of wide heads, you are giving attention to the full word.
Right. So this is also one of the, I guess, something that is not right, because we want to give attention to the words, right? Giving attention to the letters would not be that significant.
So let us see one by one that how this, because both of these heads are, sometimes it happens that you have attention, you have narrow and wide, both of them are actually being there in the network to
Okay.
learn.
Okay.
So narrow will learn the local and what is this, the other one, wide will learn the global one.
Okay, sir.
Yes,
Okay.
right. So now let's go and talk about, so we are done probably with this, what was that, self-attention. Once self-attention is understood, let us talk about what is a transformer network, because we only understood up to this, that how we can somehow find out the self-attention mechanism. Now, transformer can actually be seen as any network which is having multiple connected units, and not a very unanimous definition, but at least several places we assume that transformers are going to have these connected units, and these units are only communicating to each other via self-attention. So you only you can have units like this, and all these units, if you wanted to communicate between one to another, then they cannot communicate like this. They can communicate in a way, in between things are not communicating. Input is coming, attention is coming, and self-attention is going to be given to the next layer and next layer and next layer. So self-attentions are repeated, self-attention things are going to happen. And that is why if I show you a transformer block, single transformer block is actually being shown like this. What it is my input 1, 2, 3, 4 and so on. This is my output 1, 2, 3, 4 and so on. That is my output. This is my input. This is the transformer block. And this is the self-attention layer. You all understand what is happening inside the self-attention layer. Depending upon narrow head or wide head, you are learning WQ, WV and W query value, and what was that, key and key. So 3 matrices are going to be learned, and if it is multi-head attention, then multiple heads are going to be learned over here. So what is going in, your same thing, your same dimensions and same number of outputs you are going as an output. And then there is a residual connection which is being there. After that you apply layer norm. So the way in which we apply batch norm in neural networks, when we are talking about convolutional layers, if it is actually a type of, so I will talk about this layer norm maybe in the upcoming lecture, but the vague intuition is that you need to apply things in the layer by layer normalization instead of doing the batch normalization, because if something in terms of time series type of dependence is there, recurrent or transformer networks actually require layer normalization. More details are going to come. What is the meaning of this layer normalization and how it is different than how it's different than batch normalization. Ultimately, once you have got this layer normalization, again what you will get, the same dimensions. So whatever you have got here, whatever you have input, the same type of output you have got over here, the same type of output you have got over here. And all of them are individually going into multi-layer perceptrons. Some fully connected network is being placed. And later, you aggregate all of them. It's a single layer multiple neural network. So you can see that this network can actually be like this. So whatever go in got shrinked, and only one layer, the same thing is similar to that, is going to, same dimension is going to come out. And then you add all of them. and again you apply layer normalization. So the dimensions which are going to be there exactly same. Let us ask here that do you have, or what type of questions you have in your mind about transformer network. Please see this. This is the basic diagram of, so two things which are happening over here. First is the residual connection and second one is the layer normalization. So after doing any layer, you apply layer normalization. So whatever the features you have got attention based features over here, then you normalize them, then over that you apply multi-layer neural network, and again you normalize them, and you have got the final output, that is the representation of your input. Why? Yes, please ask me question.
Sir, here we have not used that sequential information, right? That you
Yes,
use.
correct.
So this is just a part of a transformer, or this is the whole transformer?
Not the old and not the part, it is actually in between. I just have started you to understand transformer, and yes, then I will tell that this is the drawback of this transformer, and we will have to use positional encodings.
Okay, sir.
So one by one we are going to talk about. Any question I wanted to handle, if you have anything. Can anyone tell that why do you require a type of feed forward network over here? Or residual connections over here? Let's first answer here. Why do we require residual connections over here? Any question? Somebody has written chat. Sir, I can hear. Okay, you can hear. Fine. What was, yeah. I was trying to find out someone who can be interested. Anyone can answer or discuss. See, these things are nowhere written, by the way, let me tell you. We need to figure out why do you require these type of connections over here. And we need to argue that, okay, these connections are going to be useful. So first thing is that why do you require a residual sort of connection? And then why do you require feed forward layer like this?
Sir, to kind of check, say for the first self-attention layer, to kind of check whether the output that we are getting is in correspondence with the actual input or something.
Yes, so every time residual is a standard technique. So suppose that self-attention didn't have got learned anything, or even if it is learning something, instead of learning the same thing over here, we only wanted our network to learn some residuals. That here, instead of learning something new, just learn what is different from them. See, what is going to happen is that from here to here, you are actually going to get the representation of the same things of attention. Representation of same things, but in the form of attention. This thing is actually corresponding to this guy. Okay, and but maybe exactly same, or maybe you are getting this thing in such a way so that it is being defined in terms of its own values as well as the things which are related to itself, related to this guy. So suppose that it's not related to anyone and network is not learning. If you do residual, then probably these things are directly going here. So you have not lost anything in between if self-attention is not able to learn. The residual connections are always getting or making your network learn fast, as well as things actually got regularized. Because residual, first of all, only learns the residue. Suppose that from X, you wanted to learn Y. So instead of learning Y, why I do not learn X minus Y only? So that is the main motivation behind using the residual connection. From X, you wanted to learn Y. Then instead of learning this full Y, you say that instead of that, if I learn only X minus Y, that is even better. Why to learn the full Y? So that is why you can have these residual connections over here. I am giving you my interpretation that why I feel that it's being there, because nowhere it is actually written specifically that why such type of things are happening. But usually residual, and the second thing about residual is that when gradients are flowing back and these networks become very, very big, when gradients are coming back, they are directly being, taking this route as well as this, but they can use this route, and because of that the gradient connections flow much faster. Layer normalization soon we are going to see. And the final thing is that individual, whatever the things that you have got, they are actually multidimensional vectors, can actually be shown like this, and they are being fed into a small single layer neural network, and you have got something. It's being done in such a way so that when all individual things are coming, they are going to their individual networks and being converted or transformed in such a way so that later when we add or concat all of them and apply layer normalization over them, you get certain things which can easily be concatenated. So this is actually a type of feature transformation that we are doing after getting self attention, after applying layer normalization. Whatever the normalized features that we have got in terms of attention, how to convert them into another transformed space. This is one another transformation space they have actually tried to convert them into. After that they apply the layer normalization over there. By the way, both of these techniques are very standard in normalization and residual techniques. They are actually being there. And suppose that if this is your one transformer block, I use multiple such transformer blocks, one after another. So now it's going to be that you have got one transformer block, and that is going to give you one type of embedding for your input. And instead of having one, I'm having multiple. How? Now you can see. And now this is the proper one transformation classification which is happening, transformation based classification. It's going to be a sentiment classification data set, make a sequence classifier we are going to make, and for movie reviews we are going to do it, and tokenizing into words. And it is just suppose that I am going to say it is very bad, so the sentiment is negative. If it is very good, the sentiment is positive. So this is my input sequence. For each input I have got the word embeddings, I have got the position embeddings. I add both of these, add both of them. So you have got the word plus position embedding got added, and all of them are being fed to my first transformer layer, which is being defined like this: self attention, layer norm, MLP, normalization. You will get output. So for it is very bad, which is going in, you will get it is very bad, but in the attention domain, they will go in, and then you will get it is very bad, but after second transformation, after third, after four, after five, and so on. And then this is your final attention that you have got for your input sequence. So it is very bad. It's telling that I am getting these features, and they are being learned in such a way so that all possible attention and the context everything is being learned, and these are the best possible uh, outputs that we are getting for your input sequence. How you are going to do a positive or negative classification. So I will take this. This is my feature number 1, feature number 2, feature number 3, feature number 4 that I have got after all these transformations. I do average pooling over here, that is called as global average pooling. So I apply averaging over them. Global average pooling is going to give me only one such vector, and over that you can apply some sort of softmax classification so as to convert it into a positive or negative value. Whatever the positive or negative value that you are going to get, then you will check that whether it is a good sentiment or a bad sentiment. Accordingly, you will get your loss, and then keep on back propagating. See, this global average pooling is going to give you one feature vector, one single feature vector, and over that you apply some multiple layers or single layer or whatever so as to get only one value, and then do the positive, and whatever you have got, that is your output. That's going to be, and over that you can apply softmax or something so that the thing become equal to. So here it is actually two values that we are getting, and then we apply softmax because it is going to be a positive or a negative sentiment. So whatever the global average pooled vector that I have got, I apply certain layers over that, and after at last I am getting only two such outputs, one for positive and one for negative. These are the probabilities. And then standard cross entropy loss, you can have binary cross entropy loss to train such a network. Let us have few questions over here. Anyone wanted to ask any question? 15.
Sir,
Yes.
sir, in a wide and narrow self-attention,
Yes.
in multi-head, we use in the different chunks. Can we use instead of this the different scalings, different head?
Scaling, if you want to do different type of scalings to different chunks, then scaling need to be learned properly, but that is not usually being done. That's not usually being done.
Why, sir? Because sir, in
Scaling,
the chunks, let's say there is no interconnections between each chunks, so maybe scaling will be better for here.
which type of scaling? See,
Sir,
if one scaling was root case scaling, that is anyways being done.
yeah,
And any other type of scaling is anyways being done. If you want to say, then layer norm is happening.
okay.
So layer
Okay, sir.
norm is not, I do anything, I do normalization. Yes, is that okay?
Yes, sir.
Yes, any other question? If you want to ask,
Sir,
yes.
sir, your back propagation will happen from the layer before average pooling.
See, back propagation will start from here up to this, and we know how to back propagate the average pooling layer because it's a linear thing. So all of them are going to get the same thing. If G is the gradient, then all of them are going to get the same thing because it's additive. So addition converts back propagate gradients equally in all the directions. You remember, addition equally back propagate in every direction the gradient. Multiplication invert it into the directions.
Yes,
We
sir.
have seen in the very initial lectures. So we will get our loss from here, whatever the binary cross entropy loss, and keep on back propagating. Any other question? Is it clear to everyone clearly? If it is clear to everyone, that's very good. So we are having multiple word embedding, then position embedding, both of them got added. There is a question that why you are adding, we will talk about that. Then I tell you that a few questions. How to get this position embedding, we do not know. Why you are adding, this is my second question. Third question is that you are applying multiple transformations. Yes, we are applying multiple such transformations because of the fact that we wanted to get the best possible output in the attention domain as ever possible. And after getting this, we are doing average pooling. Why can't we do any other pooling? You can do any other pooling if you want, but average pooling makes most sense, which means to say that whatever the feature I have got for it is very and bad. In fact, if I say that we have got multiple features which are representing the input. We have got multiple such features which are actually uh, representing my input, and you wanted to say something about this input, then why not to average them? You can average them, you will get something, then you can do certain other things, because this is one such architecture. You can have another architecture in which you concat all of them, or you can use all of them in a different way. You learn another, instead of averaging, you learn weights for all of them, so as to get the best possible combination of that, instead of average pooling and then do the classification. So many things can actually be done. This is one such architecture. Now, in next few minutes, we will talk about positional embedding, and then in detail we will see this positional embedding. But let us ask that what is your thought about the positional embedding, how you can get any positional embedding. Can you give me any simple way by which I can get a positional embedding? Ashima, can you tell? Ashima, you just have joined?
No, sir, I'm here.
You was here. So can you tell me that, what was the question? Positional embedding. Can you
How
give me
can
a, yes. See, this is my word number one.
the
This is my,
slides are given?
yes, say it again.
Sir, we were using the neural network to get the word-to-vec embeddings.
Yes.
So we can have a neural network to get these positional embeddings as well.
But for this positional embedding, do you require them to be related, or this relationship is very firm and anyways fixed? What is the relations that you want in your position embedding? One is related to 2, 3, 4, 5, but the amount of relationship between 1 and 2 and 2 and 3 remains to be the same, but the relationship between 2 and 4 becomes weak, but twice weak, because they are too distance far. Because this is actually that it's just a relationship that you can have between 1, 2, 3 and 4. 1 is related to 2, 2 is related to 3, and 1 is also related to 3, but not that much. It's just the distance between them, and it has to be consistent. The distance between 1 to 2 and 1 to 3 has to be somehow being managed. Delta T between two positional embeddings should the distance between 1 and 3 is less than distance between 1 and 2, or the distance between 1 and 2, if I take and multiply it by 2, then that has to be the distance between 1 and 3, and multiply it by 4 and multiplied by 3, then that should have to be the distance between 1 and 4.
But sir, sometimes we have words which are really far away, but they are more connected than the words which are near to them.
Yes, so who is going to capture that information? Word embeddings are going to capture that. Position embeddings responsibility is only to tell you that you are standing at which location. It is standing at which location. What does this it mean? It is there in the word to work or the word embedding. The responsibility of position embedding is just only to make sure that I am telling that this is the word and it is at this location. So that is the position embedding.
Okay.
Now can you tell me that what is the best possible simplest position embedding that you can have?
So we just need a function.
Yes, we require a function, but what is a simple position embedding that you can have? Simplest.
So we just need to subtract the
Yes.
location, just the Euclidean distance.
Yes. So let us go now. And we all understand that why do we require positional embedding? Because any sentence can be seen as a complex time series and having a well-defined semantic associated to it. Therefore, your RNNs are actually seeing them as sequential units, and that is why they were really slow. But transformer do not see them as time series. In fact, they used to see them as set or independent sets. So within a set, each and every the location of the element is irrespective, and that is why they were massively parallel. We just have seen that. But suppose that this is my encoder network based on transformer, this is my decoder network based on transformer, and W1, W2, W3 go into my encoder, all W2, W3, W1 go into my encoder. Output embedding is going to be almost same. Whatever the outputs that you are going to get, it's almost, it's exactly same, but a permuted version of output that you are going to get. We have seen this thing as well. And that is why we require a way, in our network, transformer networks to also pass the positional embedding. So the first thing is that you can have a decimal encoding for each and every time. Yes, just the way Ashima or anyone can understand. Your time is equal to 0, 1, 2, 3, 4, 5, 6, 7, 10,000. Some big number. And that is my positional encoding. So you can give the decimal encoding for such a things. Pratik, can you tell me that what type of problems this type of encoding can have?
Yes, sir.
Yes.
Sir, so problem.
T is equal to 0, 1, 2, 3, 4. Basically, at any time instance I, the embedding is I itself.
Right.
Is the simplest thing. Then what is the problem with such thing?
Sir, I guess as the time series increases, the number size will increase a lot.
Yes. Any unbounded function is not possible to be used.
Right.
Because it is not going to be generalized for longer length sequences. Fine. Then somebody will come and say, then what is the problem? Normalize it between 0 and 1. If
Right.
you can normalize it between 0 and 1, then it becomes bounded. So how can you normalize? You can normalize it using sigmoid or something.
Right.
So if you can normalize between sigmoid or something, then what will happen is that delta t between two things
becomes different.
Yeah, becomes different. It doesn't become, consistent the way in which positional embedding or time or any sequence embedding should have to be working for. The distance between two things keep on varying. So our few criterias are there. First, understand these criteria, and later we will understand that how can you get. Basic criteria for any encoding is position of a word. This is the most important thing. Position of any word in any sentence must have to be unique. For every time step, a unique embedding has to be generated. Distance between any two time steps, delta t, must have to be consistent across all the length sequences. All the length sequences. What does it mean? This means that suppose that you are in your data, wait, मैं सर आपको 5 मिनट में फोन कर रहा हूँ. मेरी भी, मैं घर पे हूँ, मेरी क्लास चल रही है, बस मैं आपको इसके बाद फोन करता हूँ. जी. Yes, so the first thing is that your data is going to be sometimes of length this, and other data may be of length this, some data is of length this, and some data is of length this. So if you take this length and normalize, 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 then in each and every case, what is going to happen that the distance between two units here and the distance between two units and the distance between two time and distance between two time, all of them are different. And delta t across the inputs is not consistent. That is what is being given over here. First thing is that for every time step, the encoding has to be unique. That is being the first one. And the second is that the delta t need to be consistent for every length. The third thing is that it has to be bounded and should be generalized well for longer sequence. And it has to be deterministic. Should not be any random function. It has to be deterministic and fixed for any input given length. Fixed means that if I take this much amount of length and the embedding for them is actually, I will get something. After some amount of time, again same length pattern comes, same embedding and same embedding it to be generated for each and every input. So it has to be deterministic and fixed, should not be changing for any given input length. Let us take few questions over here. The basic criteria behind encoding. Do you want to ask any question?
Sir?
Yes.
Sir, can you please repeat point 4? What signification of this?
Manvin, can you speak a bit louder? Speak a bit louder.
Can you please repeat point 4?
Point
No.
4. Yes.
Yes, sir. It has to be deterministic. And what does
Yes.
it mean?
Yes. I understood what you were trying to say is that it has to be deterministic. Yes, it needed to be deterministic as well as fixed. It should not be a random function that this time length or this much amount of length of the pattern, then the embedding is not changing. It is being fixed. Whatever you will get over here, it's going to be fixed for all of them. Probably it is that, yeah, I am getting one length this is my x1, and suppose that this is my x2. Both of them are actually of the same length. Then the embeddings for all of them, this is equal to this is equal to this is equal to this, and this is equal to this. Understood?
Yes, sir.
Yes. Okay, so with this today, I am going to stop the session.